Section 10.5 is called construction of a power transformer. So we're going to look at the physical construction of a transformer and how the design characteristics of the power transformer are used to account for the models that we looked at earlier. And we'll walk through some of what those things are as we go through this thing. So we're going to a new phase here in chapter 10, and I know you've done some, this is the first parts of this, the first 4 parts, it wasn't easy. It's a tough slog getting through all that stuff. So, this is more what we call qualitative instead of quantitative, and describe some of the things that we discussed, worked through in the earlier sections. So this is figure 10.9a, and it again, the power transformer approaches the ideal transformer. And so, how does it do that? There's some things that for that to happen, we have to account for. And the first one that he mentions in this section is the high permeability that we talked about, for the ideal transformer. How do you approach that with a practical transformer? And the way that you do that is that the core of the transformer is made of iron. It's of a laminated iron core. And because of that, the magnetizing current that we would need to create the flux that we would need is about 5,000 times less than it would be if there wasn't an iron core. And think about that core not being there and it just being air. So, because of the design with iron, it's the magnetizing ISOBM current is 5,000 times less than air. Furthermore, to keep the iron losses down, the core is laminated. Okay, and so these are laminated plates that have insulation on them, and it prevents eddy currents from actually flowing through that. And so that's how we, lessen the iron losses. Coming from this world and being associated with particulars of some of these devices, sometimes it's not just all about, the price of something, but, a better transformer is designed by, for instance, using high resistivity, high grade silicon steel, so the components and all that go into this, they actually make a difference, So anyway, consequently, he says the IS of F, this IS of F current needed to supply the iron losses is 2 to 4 times smaller than the IS of M by 2 to 4, by 2 times to 4 times less. Okay, another thing that we talked about was the leakage reactants, XF1 and XF2, and we make those as small as possible because we want to couple as much of the flux from the primary to the secondary. And so what happens is the primary and secondary coils are actually wound on top of each other, and you space these coils as close as you can. Now, of course, they're insulated from each other, right? They're insulated. You can't have, electrical conduction between different coils, but, so they're insulated from each other, but that tight, close proximity increases the coupling that occurs. And such tight coupling between the coils mean that the secondary voltage at no load is almost exactly equal to this ratio that we're very familiar with times the primary voltage. And also this idea of, voltage regulation. Once we connect a load to it, how much does the voltage drop? That sort of thing. It's much better because of that. Another consideration after leakage was winding resistance. And winding resistances, R sub 1 and R sub 2, are kept really low to reduce these I squared R losses. These are the things that cause the problem, the heating losses, and therefore a loss of efficiency. And so the winding resistances are kept very, very low. And so this figure 10.9, it's sort of a simplified version of a power transformer in which the primary and secondary are wound on one leg of the core here, right? And so the flux, flows through this core. And for the same reason, larger transformers, well, he goes in, he says, in practice, primary and secondary coils are distributed over both core legs to reduce the amount of copper. So, instead of this, it's more practical to have this actually distributed over both of these. So this is sort of a simplified version of this thing. Larger transformers, the cross section of the laminated core is not square, but it's actually built up to be round. The squareness of this is not conducive to coupling of the flux. So, that's why we see round transformers. Good example of that, right? We look on the top of a power pole and we see a round transformer. Okay, that's part of the reason for that. If you were looking at a model train or something application, you've got the transformer, those are square, but where efficiency and power is less of a factor. 10.9 shows us how laminations are built up, and you can look at that a lot better with your textbook. But these laminations are actually stacked, and has to do with the eddy currents. And then let's see, 10.9C. Now here, this is the size of this stuff that we're looking at, right? This is a large transformer with a rating of 128 kilovolts, 290 amps, and you can see the primary winding of a much larger transformer here. The number of turns on the primary and secondary windings depend upon their respective voltages. A high voltage winding has more turns than a low voltage. On the other hand, the current in the high voltage winding is much smaller, enabling us to use a smaller size conductor, okay? As a result, the amount of copper in the primary and secondary is about the same. In practice, the outer coil, coil 2 in this, the outer coil here, see if I can show us that. The outer coil here weighs more because the length per turn is greater. Okay, so it's the circumference is more because it's larger. But anyway, aluminum and copper conductors are primarily used. And another thing that's kind of interesting, and I've actually experienced this, and if we were meeting in person, and we would do this in a lab, but a transformer is reversible, and in the sense that either winding can be used for the primary or secondary. The primary is defined as what's connected to the source. So we could take a step-up transformer with one connection and use that same transformer and reverse and connect the voltage to the other side and make it a step down and vice versa. So, that is, the transformer is reversible, and that sort of concludes this general qualitative look at the actual construction of a power transformer.